Hello, everyone. We are Group 7, and this is our final demo presentation, and we will be going over our senior design project, which is fluoride level observation in drinking water, also known as FLOW. And now we will go over our team members.
Hello everyone, my name is Elisa Johnston. I'm a photonics engineer.
Hi everyone, my name is Nahito Dorval. I'm a computer engineering major.
Hello, everyone. My name is Nyla Seymour, and I'm a computer engineering major.
Hello everyone, my name is Obane Lennox. I am an electrical engineering major.
Our flow device is a portable, cost-effective tool designed to monitor fluoride concentration in drinking water in real time. It uses fluorescence-based detection to measure the fluoride concentration levels. Our working components are the laser module, which is the 532 nanometers, plastic cuvette that holds the sample, a long pass filter that blocks the laser light while transmitting the fluorescence emission, plano convex lens for the detector, the full TSL 2591, which is to send the data for processing, a PCB microcontroller, and our power supply, which uses a USB 5 volts.
No, we are using a laser. So we have a 532 nanometer green laser, and this laser is directed into the sample, which holds our fluoride concentration. We put the sample in our cuvette. Our cuvette now goes into our device, which we have a little circle. It's a square, which holds the cuvette. And the cuvette contains fluorescence dye, which is rhodamine B, and a specific milligram per liter of fluoride. This dye will allow us to absorb the light laser, and it emits the fluorescence at a longer wavelength so that we can pick up on the emitted light. This light goes through a long pass filter, which is placed in a perpendicular way to the laser so it can block the scattered laser light, and I can isolate the fluorescence. Now, this filtered fluorescence we will be able to pick up through our lens, which is then detected through our photodiode, also known as our photodetector, which we have within our device. And this picks up on the fluorescence intensity, which will then display as our specific fluoride concentration.
We all know that fluoride plays a vital role in preventing dental cavities and promoting bone health. However, maintaining safe consumption levels is critical as excess fluoride can lead to serious health problems. To solve this problem, we are designing a portable, a reliable device that uses fluorescence-based detection to measure fluoride concentration with high accuracy and reliability.
Our goals for our project was to build a detector that can accurately detect and measure the fluoride concentration in drinking water. Also, the advanced goal for that was to develop a calibration system for the detector to ensure accurate fluoride measurements in the drinking water. And our stretch goal for that was to design a housing device that's easy to carry and to use in different locations. The design and housing for the device is tightly sealed to prevent stray lights from interfering with the measurements. And we added a Bluetooth feature to it so we can talk to it wirelessly. And that our software interface with the additional sensors for detecting other contaminants, providing more comprehensive water quality and analysis. Um, our software development was to collect and display the fluoride concentration readings in real time. And the design was our PCB design prototype was to satisfy the power delivery requirements for the fluoride detector system. Our objectives for our project was to integrate the sensor and calibrate the sensor using the standard fluoride solution to ensure that it meets our desired accuracy. Our stretch goal for that was to create the calibration protocol using the fluoride concentration and to make sure that the device could calibrate the regularly maintain accuracy. And our advance was to focus on the compact design that protects the device during the transport. to other environments. And our housing design was critical for our it was is critical for our device accuracy, and our device process involved like a 3D modeling printing to make sure that the housing provides a dark environment for the sensor, and we updated the PCB to make sure I can interact with it with the Bluetooth app, and yeah.
For engineering specification, our top three, we have like a laser module that will have a 532 nanometer wavelength. This is effective for excitation of the fluorophore, producing a fluorescence emission peak at 566 nanometer. We also have the long pass filter that has a cut-on wavelength of 570 with a bandwidth of 6 nanometers. It blocks the 532 nanometer laser light while allowing fluorescence emission at 566 to pass. Also, another one is the photodetector Adafruit TSL2591 with a full spectrum and infrared sensitivity. It's sensitive to the fluorescence emission at the desired emission wavelength. For our hardware block diagram, we can see the power our laser module, and then we have the excitation and emission system that will also the detection stage and the processing and output. For our optical diagram, this is where our optical design comes from. We started with the dichroic mirror. It has like we use with the dichroic mirror, it separates laser excitation and fluorescence emission by reflecting the laser wavelength of 532 while transmitting fluorescence at 566. The advantages is kind of like reduces interference from scattered light and simplifies signal isolation. The disadvantage with this is that it increases complexity, and also with our tight budget, the cost is very expensive. It's almost $400. So we wind up using with the design without the correct mirror, but it's still the same function that relies on the long pass filter to block the scattered light and transmit fluorescence emission. The advantage for this is it's simple, more compact, and also cost-effective design. The disadvantage is it has a greater reliance on the filter quality and precise alignment to minimize the noise. For lens consideration, we have the plano-convex lens, a chromatic doublet lens, and a spheric lens. With this, we chose plano-convex lens. It minimizes the spherical aberration for our focusing light. It requires precise alignment for optimal focus. So we acquired Thurlob's plano-convex that has a focal length of 30 millimeter. That is ideal for our project, and also a diameter at 24.4 millimeter. For our light source comparison, we wanted to do the laser diode, but we also had in mind for the laser module with the laser, and we wound up using the laser module because it includes the diode, the optics, the driver, and the cooling. It's also easy to use. We don't need any external circuitry. It's also already pre-collimated and has integrated heat sink. So we picked this green laser module over here. That has a wavelength of 532 nanometer and a divergence of 0.6 milliradian. So, and also with an output power of 5 milliwatt. That is ideal also for our project. For our filter consideration, we had like the band pass filter and the long pass filter. We wind up choosing the long pass filter again because it's cheaper than the band pass filter. and have we got the one from Edmond Optics that has a transmission of 93%. For our cuvette, we started with for our first testing, we started with quartz cuvette, but we need 9 cuvettes for our testing and calibration. And it's too expensive. Just for 2 cuvettes, we would have spent $30, and we had 6 and we need 9. So we, for our final pick, we did the plastic cuvettes because there's really not much of a difference. It's also cheaper, and we could use several of them without having to use more of our money.
BOM, also known as Bill of Materials. The cost for our components were $35 for the laser, 103 for a cuvette. The long pass filter was about $93. The lens was 78. Photo detector was about $6. Display was $15. PCB was about around $220. Our fluor fluorophore was 18. Fluoride solution was 43. Housing was 40. So which was a total of $652. Work distribution was pretty evenly distributed. We had the optical design for Alyssa. Hardware selection was by Alyssa also. Software design was between me and Nyla. And display also. The PCD design was to O'Dane, and the housing was done by Alyssa.
PCB microcontroller selection. We wanted to go with uh, microcontroller that was pretty flexible, and it had Bluetooth enabled features. So the ESP32 Room 32D was a optimal choice for doing that. It also allowed to use the Arduino IDE development software, which was familiar with the group. So that was also another choice as to why we chose that over the other available option. In terms of also just the flexibility and just capability of the processing power of the chip itself. For the PCB layout, originally the PCB layout consisted of the bridge, and it had a linear regulator, and they also had a switch-in regulator. Unfortunately, one of the regulators just wasn't able to really get it to work, and we ended up switching out that switch-in regulator to and just use 2 linear regulators. And the reason for that was primarily because it turns out we didn't need that additional high voltage that the switching regulator would provide. So the linear regulators were sufficient enough, and then we had the peripherals like the tactile push buttons, the pin headers, the LEDs, and then we also had our ESD protection circuits. We went for the option of using the micro USB, and then we had diodes, resistor, capacitors, inductors, and everything else. And then, okay, for the PCB board, went with a 2 layer option layout, and we had did an isolation of 20 mils to provide enough spacing. The thermal was 20 or so with a global width of 15, and we kept all of the signals at a minimum of 10, and then all ground and power were set at a standard 15 mil. Um, so the PCB boards, we ended up doing 2 iterations. Uh, the one on the left was the first iteration. That one was the original board that we used to test uh, and to see what was going on, what was working, what was not. As I said before, the boost switching regulator was not working. We also had a MOSFET on there that was completely ineffective. And then also we had some minor wiring issues, as you can see the wiring on the left right there. Uh, One of the circuit wasn't connected correctly, and so we had to reroute the circuit to get um, to supply enough power where it needed to go to the node to make sure the distribution was stable. And then everything else pretty much stayed the same. That transition over to the final PCB board. The only difference is we switched out the regulator for linear. We added some more pin headers because it turns out we needed additional pin headers for the photo detector and the display. So that's why there's more pin headers there. And then pretty much most of the stuff stayed the same. We kept some more space in to give some more for more heat dissipation. But overall, the board didn't layout didn't change that much.
Like O'Dane just mentioned, our microcontroller that was used by myself and Nihito was the ESP32 microcontroller. During our testing phases, when we were going through prototyping and trying to figure out how we would work with our IDE, the ESP32 was the most reliable and common source that was also user friendly for what we were trying to accomplish. So with that, it had built-in Wi-Fi and Bluetooth. And that was very important because we wanted to be able to control our device uh, portably so that we'd be able to set certain commands without being in the terminal. It also is versatile with different interfaces. So it has built-in SPI, I2C, and UART support, which is very important for the amount of data we'd be configuring. It also has low power modes, so it will help conserve its own energy. And it's really, really, really important because our device obviously has different um, power that it's being received in different aspects. So we want to make sure that it would be able to have that self-efficiency. So for our photodiode, we are using the Adafruit TSL2591. And we chose this because it has a very dynamic range. It goes from 1 to 600,000 lux. Our lux values is the values that are crucial in us figuring out how much fluoride is in our samples. When we receive our lux values, we'd be able to figure out the light intensity from our emitted light. And that goes, it's very, very hand in hand with our fluoride concentration values. So that was really important. And then also having that digital interface is very important with the I2C interface, which would go hand in hand with the communication of the ESP32 microcontroller. Um, and then it also has low power consumption. All the devices that we try to have has this, and we wanted to make sure that we weren't overheating our device, so we chose something that had low power consumption. Our display. So we chose the Adafruit I ILI 9341, and we were able to display all of the fluoride concentration on this device. It comes with touchscreen capabilities, and it's very flexible. It has a lot of the libraries built into the Arduino IDE, which we will get to in a second. It has a very high resolution rate. It also has great brightness. And then it's able to put in real-time data and present real-time data, which was very important for us because when our photo detector came in, we wanted to make sure that we would be able to relay that data in real time. But also, it's very cost effective. We were able to order our display for $15, which was very important to us because we had to stay en route with our budget and in reflecting of our bill of materials. So like I just said, we use Arduino IDE, and this is because Arduino has a history of being just a very easy to use, user-friendly workaround environment, especially when we're doing such high level things. It's very important that we have a library that supports all of our needs. So Arduino has a very extensive library support for the ESP32 microcontroller, which is also why we went with that microcontroller, as well as for the photodiode. And then also there's a lot of compatibilities across platforms, which would able to support all of our operating systems and flexibility for all of our team members. And yeah. So as you can see here, this is our software diagram. And this software diagram is our general software diagram, which shows how we were able to achieve our fluoride concentration displays for our device. Now, these are smaller subset diagrams. So on the left, you have our user interface, and the user would allow the device to turn on. So through the BLE connection, which we'll get to in a second, you'd be able to power on the device and store data, to collect data, display results through all those commands. And then they would process that data and be able to also save, send, and show results. For our state diagram on the right, we have how our device is powered off, and when the device is powered off, like I said, through our BLE connection, we can turn the device on. It would be idle, so it would mean that it would not be in a ready state, but we can create it to be in a ready state by calibration, by collecting data, by storing data and transmitting data, depending on what we would want the device to do. And then it'd be able to process that data and display those results and then go back to its powered off state through the BLE device. So we have our data transfer diagram to the left. With the photodiode is where we get our first layer of data with the emitted light the photodiode picks up on. So through the photodiode, it changes the analog signal to ADC and then digital signal, and that digital signal will show up as our lux light intensity values, and that will show up through our microcontroller. Our microcontroller would be able to convert those signals so it could be stored on our side through our terminal, and then we'd be able to process that data and see how it's being read through our display. On the right, we have our class diagram. And our class diagram just goes through how we're able to display our data, input raw data, and store raw data, calibrate our data to show our calibration curve, and just timestamp data with our process data, transmission data, and store data.
All right. So through our BLE app, we'll just through our code we made a portion where we had to make sure that we establish a name for the device, and through our BLE app, we tried to see if we can find the device. And when we do, we select it, and through there, we press customize characteristics. Through the customization of the characteristics, we get to write, notify, or our values, so our um, commands, I would say. And from there, we are able to send our commands through the device, and we tell it to either to turn on, turn off, just the device, just all the commands that Nyla previously stated. We're able to do all those things with the app, which is very helpful for our device to be more for the ease of use of our device.
For testing a device, our testing consists of 9 different samples, as I mentioned earlier. We have like from 10 milligram per liter down to 8, 7, up to just the distilled water. We gather our lux values from our emitted light through our photodetector and find the fluoride concentrations from our cuvette samples. The fluoride concentration then displays on our device once it's find the right concentration of that sample. And that would be all for our flow device. And thank you for your time.